Swayam Prabha. Digital India. Educated India.
In this lecture, let us discuss about non-equilibrium chemistry. We will recapitulate the chemical non-equilibrium concepts and the chemical rate equation very briefly, because we have covered all these concepts elaborately in an earlier week, and later on we will look at Park's two temperature model. The chemical rate equation, which we had discussed at length in an earlier week, we are just going to recap the main points here. We once again recall that molecular collisions are absolutely essential for chemical reactions to take place, and if you consider the dissociation of molecular oxygen as a test case, if you are raising it at 1 atm pressure from temperature of about 2000 or 2500 Kelvin onwards to up to 4000 Kelvin, you will see a gradually dissociating gas, and if you do not allow it enough time to settle to its equilibrium conditions, then you will be basically taking it through a non-equilibrium situation. The molecular or atomic oxygen concentrations in the mixture keeps changing with time if it is a non-equilibrium situation, and therefore, like we saw in the case of vibrational energy exchanges, even in case of chemical reactions, we would need a rate equation to be worked out. We recall the distinction between chemical equilibrium and chemical non-equilibrium in terms of reaction rates. The main underlying idea is that in chemical equilibrium, you have a zero net rate. That means, the forward and backward reaction rates exactly equate with each other, while for a non-equilibrium situation, they would end up producing a net rate which is non-zero. And we are talking about a reaction where oxygen is dissociating. There is a collision partner which is involved, which could be molecular oxygen or atomic oxygen or molecular nitrogen and so on. Finally, we find that the collision partner remains unaffected while the molecular oxygen dissociates. And earlier, when we were discussing about equation of state, we used the nomenclature C for concentration of a pure gas or Ci for species in a gas mixture. In the equations for chemical non-equilibrium, the concentration of different gaseous species is indicated using a square bracket. So, it is essentially a nomenclature issue. When it comes to forward reaction, backward reaction and correspondingly the reaction rates, then we involve forward reaction rate constant, backward reaction rate constant, and we look at the forward as well as the backward reactions hand in hand, and we try to figure out which is dominating over the other, and that essentially gives rise to the net reaction rate. So, starting from this, if you write down the rate equations, they will ultimately evolve in this form, but for that we need to understand the general chemical reaction format for all elementary reactions, and we recall the definition of elementary reaction. It is one that takes place in a single step. Oxygen dissociation is one such reaction, and therefore, it can be considered as an elementary reaction. When it comes to detailed analysis of this dissociation, when we consider the forward reaction, for example, if you take any species xi for example, then the calculations are done using a formula like this, where you have to find out the stoichiometric mole numbers of the reactants and products respectively, the reactants with a single dash in superscript, products double dash in superscripts, and you are essentially talking about identifying the coefficients associated with each species, whether it is a reactant or a product, in the sense of a stoichiometric mole number. Those are the ones which get plugged in here. Importantly, the sign over here matters, and then there is a product of the concentrations of the different species involved raised to the index nu I dash for the reactants here, and when you try to look at it from the reverse reaction rate point of view, you will have a nu I double dash working in this index. Importantly, there is a negative sign over here, the backward reaction rate constant is involved, and so on. Therefore, if you follow this general format and you try to plug it in for the oxygen dissociation reaction, then you will find that it finally comes up in a form like this, where we follow that general format. If you recall, a positive sign here, the forward reaction rate here, the nu dash single dash working in the exponent, and the forward reaction of course involves the reactants here. Similarly, in backward reaction you will have to notice this sign here. You have to notice that this has to contain the backward reaction rate constant. You have to take the products and raise them to suitable indices coming from the stoichiometric mole numbers of the products, and consequently the final expressions come out like this, from where again the net rate equation can be derived, because you take a difference between the forward and the backward rates, and you ultimately end up getting a net rate, and that is what is the non-equilibrium net rate equation or law of mass action, again valid only for elementary reactions only. This gives you the general framework. When applied for oxygen dissociation, we find that the equation boils down to this form. So, this gives us a very nice general framework with which we can proceed to analyze other elementary reactions too, and we would be very keenly interested to do this for the different species involved in high temperature air. If we try to connect the situation with an equilibrium situation, then we need to allow enough time for the collisions to take place and for the chemical equilibrium to be actually achieved, and then the rate equation essentially ends up getting a 0 value, because the rates of the forward and the backward ones exactly balance each other, and then we have the perfect equilibrium concentrations of the reactants and products indicated with asterisk sign in the superscript. If you rearrange the above equation, you will get an expression for the ratio of the forward and backward reaction rate constants, and essentially this ratio is valid for non-equilibrium too. If you were to do that, then you end up getting the expression that we see over here for the oxygen dissociation reaction. Therefore, this is the equilibrium constant based on the species concentration. The equilibrium constant that we defined when we were discussing equilibrium chemical reactions was defined based on the partial pressures of the species which were participating in the equation. And you recall that we used a product of these terms where partial pressures were raised to the stoichiometric mole numbers, and we had set the pressure to 1 atm, fixing it. Correspondingly, the equilibrium constant Kp which came out was purely a function of temperature. And we considered the generic chemical reaction in this form, where we shifted the reactants to the right hand side and correspondingly took care of the change in sign, where the reactants took up negative values for news and the positive values of news were retained for the products, and they were associated with their respective species. Now, when it came to connecting these coefficients, we connected the one based on concentration and one based on pressure using the conceptual connection between the two, where we use the equation of state P I equal to C I R T, which relates the partial pressures and concentrations of the different species in a chemically reacting gas mixture, and you can show this relation between K C and K P. Since K P is known, using the above equation K C can be calculated. K P is essentially known from your statistical mechanics and thermodynamics concepts that we used based on the partition function, which we have discussed at length earlier. And then if you go back with this concept to the dO dt equation, O being the concentration of atomic oxygen, we can now write it in a form like this, where we see that the Kf is obtained from experiments, Kc has been obtained from Kp, the Kf values are obtained, the Kb can be obtained now from this relation. So, the connections are recapitulated, which we have studied earlier, and we recall that all these constants that we are talking about, the chemical rate constants, are functions of temperature. Then came an important equation, the Arrhenius equation, which is often used to express reaction rate constants as functions of temperature by using experimental results, and we saw some functional forms here, K equal to C e to the power of minus epsilon A by K T, where epsilon A happens to be the activation energy. Another possible form was this, where number of those coefficients were actually obtained from experiments. You will later on see in this lecture that this form has been used in literature. The forward reaction during oxygen dissociation, there is a 0 point energy difference involved between products and reactants, and the dissociation energy is the energy required to dissociate the molecule at T equal to 0 Kelvin. This is a non-zero quantity, as considerable amount of energy is required to break a molecule into its constituent atoms. For the backward reaction, which is essentially a recombination reaction, no relative kinetic energy between the two colliding oxygen atoms is required to bring about the recombination into the molecular form. The collision partner rather carries away some energy that is given by the two colliding oxygen atoms when they are recombining into O2. Hence, the recombination does not need any activation energy, and therefore, the functional form simplifies. Then, with all these concepts in place, we finally looked at high temperature air in chemical non-equilibrium, and we considered several chemical reactions which could be categorized broadly into dissociation reactions, bimolecular exchange reactions, dissociative recombination reactions. We had discussed about these at length in the previous week's lectures. So, for the details you can go back to them once again. and for each equation, as you notice that there are forward and backward rate constants involved, and we have 7 of them over here. This is an important juncture where it is important to recall that how do the calculations for equilibrium reactions and non-equilibrium reactions compare. For equilibrium reactions, the chemical reaction equations have to be independent, while for non-equilibrium they do not need to be independent. The number of independent chemical reaction equations is strictly specified here as Ns minus Ne, where Ns is the number of species, Ne is the number of elements, while in the non-equilibrium side the chemical kinetic mechanism may contain a large number of elementary chemical reactions, all of which have to be tracked and included, while they may not be independent with each other. Then we saw that for obtaining the chemical rate equation for NO, we have to involve all such equations which are associated with its production or destruction, and they would therefore influence the rate equation for NO, and accordingly we chose them and proceeded with the net rate equation. We analyzed all of them one by one, the ones which affect the ddt of NO concentration, did the calculations of the stoichiometric mole numbers finally, and after all that was done, we got the net reaction rate of NO, which was expressed in a form like this. So, without further elaboration, we just took a very quick touring of the concepts which are associated with non-equilibrium chemistry, and we try to proceed with these ideas in mind for some more discussion on this topic. So, like we did for NO, we can write similar rate equations for the other species that were considered for non-equilibrium high temperature air, and in non-equilibrium chemistry analysis, all possible chemical reactions which are relevant for the chemical kinetics have to be carefully accommodated or included. They should not be left out, and the rules for choosing chemical reaction equations is also different from what we do in equilibrium chemistry. And the equations that we considered earlier for high temperature air were basically confined to below 9000 Kelvin, where ionization effects were small or negligible, while if we consider temperatures which are well above 9000 Kelvin, then we would have to further consider ionization of the atoms to take place, and consequently we will have a more complex kinetic mechanism to be considered. Such reaction mechanisms along with their appropriate chemical reaction rate constants are available in several references. We have marked one of them, that happens to be a NASA report. There are several other references where such data is available. We would discuss one more, which is authored by Park in a little more detail in the upcoming slides. A word of caution that needs to be kept in mind is that there is always some uncertainty in these published rate constants which are associated with high temperature chemistry. The uncertainty arises because they are very difficult to measure accurately using physical experiments. Mainly shock tubes are used for obtaining such data, but since they run for very short durations, obtaining reliable experimental data is always very, very difficult, and accuracy of such data is questionable. We have, for example, included one such rate constant model, which is essentially found from the reference that we were talking about in the previous slide, where the forward rate constant has been mentioned, and we try to look at a typical ionization reaction which might occur beyond 9000 Kelvin or so, and for that particular reaction where atomic oxygen ionizes with the collision partner being an electron. The relevant parametric values which need to be plugged into this rate constant model are mentioned over here. The values of Cf, Cf happens to be a very large number with 10 raised to the power of 31 order, and eta f is a rather small number which comes up over here in the exponent of temperature. Kf again here in the exponential term, which happens to be a fairly large number, but that is in a negative sense there in the exponent. And we do recall about the Arrhenius equation that we visited some time back, and you can clearly see the form that we talked about over here correlates rather well with what we are talking about with the form given on the top of the slide. Next, let us have a look at the two temperature kinetic model of Park. Let us try to look at the basis of this model. What is the justification behind studying this model? The translational temperature is a measure of the collective translational energy of the particles of a gas, which we express through the E translational equation, which is given here. It exists in the collision frequency expression as well. So, it is the same temperature that we talk about when we look at this proportionality between Z and pressure and temperature. As a consequence, the vibrational relaxation time tau is a function of T. It is also a function of pressure, and so are the chemical rate constants. So, we recall about the vibrational relaxation time equation here. We clearly see the dependence of tau on temperature, which is again the translational temperature that we are talking about. It of course is also dependent on pressure, but the temperature connection is what we are more concerned about over here. And just a few minutes back, we already saw that the chemical rate constants at different temperatures, especially the very high temperature situations where ionization might also occur, we discussed in the previous slides. And you clearly see the dependence of these rate constants, the chemical rate constants on temperature figuring through these correlations. And the model that we are talking about, which has been proposed by Park, has been mentioned in his famous book, which is related to the non-equilibrium hypersonic aerothermodynamics. It is a 1990 publication which you need to take note of, and we are essentially trying to talk about a two temperature kinetic model that he has proposed, and let us try to understand what that is all about. If we consider that both vibrational and chemical non-equilibrium simultaneously exist in a mixture of gases, there is a coupling between the chemical reaction rates and the vibration relaxation rates. So, you have to be carefully watching the terms. On one hand, we are saying chemical reaction rate, on the other we are saying vibrational relaxation rates. Why are we talking about both? Because we are saying that there is a simultaneous non-equilibrium of both vibrational as well as chemical energy exchanges. Molecules in the higher lying vibrational energy levels that are highly excited vibrationally are more readily dissociated by molecular collisions. It is understandable that we are talking about much high levels of energy, and those molecules which are residing in those very high energy levels can be rather easily induced into chemical dissociation when they undergo molecular collisions. That is precisely the point we are trying to make here, and this is because they require less energy exchange during collisions to dissociate. So, you can more easily induce them into a dissociation. Therefore, this in itself explains how vibrational relaxation rates and chemical reaction rates can get coupled. So, they are inherently going to get interlinked with each other. As a consequence of this coupling, it is obvious that the chemical kinetic rates for dissociation are going to be faster if the gas is already highly excited vibrationally. This is the obvious connection that is coming up. Again, since dissociation will occur predominantly from the higher lying vibrational energy levels, there would be a reduction in the population of the higher lying vibrational energy levels due to the ease of dissociation from those levels. This would in turn affect the instantaneous vibrational energy of the gas and the vibrational relaxation time as a consequence. Therefore, it all gets coupled up. The precise accounting and calculation of this mutual coupling phenomena of the vibrational relaxation rate and chemical reaction rates is very complex, and it demands a simplified modeling, and that is precisely what Park attempted to do. So, Park proposed a two temperature model that defines a vibrational temperature T vibe followed by an average temperature T A. The average temperature is defined as the geometric mean of the vibrational temperature, that is T vibe mentioned above, and the translational temperature, which we indicate as T. Let us proceed with the discussion. A molecular species has to be considered for our discussion. Let us say it is molecular oxygen or nitrogen. If the instantaneous non-equilibrium value of the vibrational energy per unit mass of this species is indicated by E vibe, it can be defined by the vibrational rate equation, as we have already discussed. Having said that, once we know that value of E vibe locally at an instant of time, we can define an instantaneous vibrational temperature for that species based on the following equation. So, you know this from the rate equation, you plug it in here and you try to figure out which value of T vibe will satisfy this equation. Once you get T vibe, a local Boltzmann distribution of the particles over the vibrational energy levels corresponding to temperature T vibe can be obtained from this equation. The higher the value of T vibe, the more the number of particles in the higher lying vibrational energy levels. This means it would be easier and hence faster for the gas to undergo dissociation, like we have mentioned before also. To account for this augmentation effect on the chemical rate constant, Park suggests that the instantaneous vibrational and translational temperatures be combined to form an average temperature. So, that is how he comes up with an average temperature definition, which is based on a coupling of the translational or translational rotational temperature and the vibrational temperature, which is essentially an instantaneous non-equilibrium value, but we use the Boltzmann distribution locally to give you the kind of population distribution. So, there comes the two temperature model that we were talking about. The T A based on the above equation has to be used rather than the T to calculate the chemical rate constants. So, this is an important input. We should not continue to use the translational rotational temperature, rather use the average temperature proposed by the Park model in order to calculate the chemical rate constants. When the gas incidentally is in vibrational equilibrium, T vibe will be equal to T, hence the average temperature comes out to be T itself. Therefore, it clearly indicates that only when vibrational non-equilibrium exists would you end up having a T A other than T. If the local non-equilibrium vibrational energy is higher than the translational temperature, rather this should be temperature, the local non-equilibrium vibrational temperature being higher than the local translational temperature or local equilibrium value of that. Then if you plug that T vibe into the TA expression, obviously the TA comes out to be greater than T. As a consequence, the chemical reaction rate for that species will be faster than if vibrational equilibrium existed. So, that is how the augmentation is taken care of through the model. Similarly, if the local non-equilibrium vibrational energy is lower than the local equilibrium value, then automatically the average temperature will fall below the translational temperature. Consequently, the chemical reaction rate will also become slower than if vibrational equilibrium existed. So, this is how the Parkes model essentially functions. Park, in order to generalize the model, sometimes proposes use of different coefficients other than purely the 0.5 or half index that we see through his basic model. So, you can think about a more general model where you propose the T vibe value to be raised to some index m, the T to be raised to some other index n, which are close to 0.5, not exactly 0.5. If you fit this model into some example cases, we look at oxygen dissociation, for example, where the collision partner that collides with the molecular oxygen is also O2. You will find that there is a dissociation and the corresponding rate equation where the average temperature has been plugged in comes out in a form like this, where if you recall that this is more of a general form which we have seen earlier, where there is some kind of a coefficient here, there is a temperature term raised to an index, then another exponent term where temperature happens to be there and in the denominator. Similar rate expressions are available for nitrogen dissociation, and you can see that molecular nitrogen dissociates to atomic nitrogen, and the rate expression in that case comes out in a form like this, where there are differences in the coefficient in the exponent for both the terms, and the units for the rate expressions happens to be centimeter cube, mole inverse, second inverse. The above equations, which form a part of the kinetic mechanism for high temperature air, along with the associated rate constants, have been taken from the book of Park. We have mentioned that reference in an earlier slide, so please have a careful look at that. Let us try to conclude. In this lecture, we recapitulated the concepts of chemical non-equilibrium and chemical rate equations. We discussed the temperature dependence of rate constants. Further, we learned about the two temperature model of Park, which addresses the issue of the coupling between vibrational relaxation rates and chemical reaction rates. Thank you.